An organic compound containing at least, so what are halides again? So as you see in this table, the 7 group elements, fluorine, chlorine, bromine, iodine, statine, these are all halides. All of them are collectively symbolized by the letter X. So as you know from the past, we talked about them, that they are very strong in attracting the pair of electrons toward themselves, because in their outer shell, they have already 7 electrons, and then they need only 1 electron, so that's why they are very thirsty for that. If you compare them to the whole table of the elements, they are stronger than all of those. They are almost siblings for the, noble gases, which has 8 electrons in their outer shell. So they have a tendency to become octet, to become 8, to have 8 electrons in their outer shell extremely strongly. So that's why they are studied as a chapter, because they have this distinguishing feature of grabbing or attracting the electron easily from any other atom within, no matter alkanes or alkenes or alkynes. If they react, they would displace hydrogen easily, because hydrogen here, it is so much electron poor, but it is not as electron poor as 7th group. They have high affinity than hydrogen. That's why when they face hydrogen, they easily displace hydrogen, they kick out hydrogen, and they make bond directly with the carbon. This is what their property is about. So an organic compound containing at least 1 carbon halogen bond or CX bond, the X could be fluorine, chlorine, bromine, iodine. This replaces hydrogen easily. A compound can contain one of them, or it can contain many of these bonds between carbons, the backbone carbon, and those fluorine, chlorine, bromine, iodine. Properties and some uses. Why this is important? Halides are important because they are fire-resistant solvent. So if you see a fire, if you use methylbutane, again, although bromine is in 5th carbon, why do we mention it first, not 2nd? Because that alphabetical order B, C, D, right? So 5-bromo, 2-dimethylheptane. And then here, as you see, we have the 7th carbon backbone, and then the 7th carbon backbone has 2 methyl groups and 1 bromine. So this time the bromine is in the 2nd carbon, but the methyl groups are in 5th and 4th carbon. Bromo still stays there. It's not because of the 2nd carbon, it's because of that B, which makes it to come earlier in alphabetical, from alphabetical order perspective as compared to the D here, right? No matter it is closer to the end or far from the end, this is the alphabetical order that we follow basically. These 2 examples are given to distinguish that case. And then begin at the end nearer to the substituents whose name comes first in alphabet, right? So here we have a case of 50-50. And the 2nd carbon, there's a methyl carbon, there's a methyl group, and then if you go from this side, in the 2nd carbon we have a bromine. So a 50-50% chance of starting from the left or right. But again, why do we start from the right side? Because of that alphabetical order. We say 2-bromo, 5-methylhexane. We cannot say 5-bromo, 2-methylhexane because of that alphabetical order.
Can you go to the back slide to that one?
Yep.
So what determines there is the alphabetical order. Why don't I go for 1, 2, 3? On the 3rd carbon, I have a bromo.
Mm-hmm.
Why don't I name it from there if it's alphabetical?
Well, alphabetical matters when you have a 50-50
Okay.
chance of doing so.
So-
Otherwise, whatever carbon
It's
is
closer to-
branched, that would be the near end for starting. Good question. Now, here we have the structure of alkyl halide. The structure of alkyl halide, which is symbolized as CX bond, is longer as you go down the periodic table. So, for example, here we have the fluorine, and then we have the chlorine, bromine, iodine. As you go down the table, the bond that they make with the carbon becomes longer and longer. For example, and here we have fluorine, which is up in the table, right? So the bond, the distance of this fluorine with the carbon, with the relevant carbon, is 139 picometers. And then if it is chlorine, instead of 139 picometers, it's 178 picometers. If it is bromine, that's 193. It increases. And if it becomes the iodine, the fourth one, it is 214, right? So the bond length gets increased as you go down the table within the group 7 elements. So, and then as you get the distance, what happens to the strength of the bond? You see the strength of the bond gets decreasing from 552 to 351 to 292. So which means the strongest bond is at the top, right? Because they are very close to the carbon, adjacent to them. And again, what is the consequence of that with respect to the pair of electron? CX bond is polarized with partial positive charge on carbon and partial negative charge on halogen. Halogens are negatively charged. Why? Because they have the tendency to grab that electron close to them, to their outer shell. That electron comes with a consequence, and that is the negative charge of the electron. So that's why the halogen appears with a negative charge. Now this electron is grabbed from the carbon, leaving the carbon with that empty space for the electron, creating a positive charge on the carbon. So that's why it has well, these halogens, they have the most polarized type of bond in all organic chemistry, because they displace the pair of electron dramatically as compared to any other type of molecule that we study, because of that electronegativity that we talked about there. And then let me take this down. So, preparing alkyl halides from alkenes. So as you know, alkenes, they have a double bond. Like here, we have 2-methyl propene, right? Meta-eta propa, because of the double bond propene. And then in the second carbon, we have a methyl group, 2-methyl propene. If it reacts with hydrogen chloride, right, or hydrochloric acid, that's what we say commonly. So we have a halogen here, the chlorine. We know it easily displaces the hydrogen. So what happens is the final product, double bond is broken. We see chlorine making a bond with this carbon, and then the number of hydrogen from 2 increases to 3 because the bond broke. This hydrogen comes here to make it CH3. So we have 2-chloro-2-methyl-propane, right? So here we are told that the chlorine is not added to the terminal carbon. And why? This is not formed. Why? Because here the carbon, has that electron density much more higher. The electron density is higher with respect to this carbon as compared to the terminal carbon. So that's why chlorine goes to the location where it gets that thirst, where it can fulfill the thirst of electron better. That's why it goes to that carbon, because the two carbons are different from an electronegativity perspective. And then, again, if you have a ring format of alkenes, as you see here, pentene, bromine, a molecular bromine easily can go and break the double bond, and two bromines would sit on the two neighboring carbons. And then you remember they are in trans. Why? Because they repel each other if they are on one side of the carbon. So they make that trans format. And then preparing alkyl halides from alkanes. You know, alkanes, they have a single bond with in the backbone carbons, so they are not very much active. But since they are facing halides, halides are much more active. That's why halides can displace the hydrogen from alkanes. Otherwise, alkanes are not very much active. To be honest, alkanes, the only reaction happening in alkanes is with halogen. Other than that, hydrogen is strong enough to maintain its position with carbons. But when it comes to halogens, they cannot resist, because halogens are more electronegative and they easily displace that. So, as you see here, we have methane reacting with chlorine, molecular chlorine forming, you know, that one chlorine containing methane, 2 chlorine, 3 chlorine, 4 chlorine, which means the density of chlorine, as it gets increased, it starts displacing all the hydrogens. So, but this creates a situation where it's not reliable. For example, you need that specific methane with 2 chlorines. You cannot extract that easily because all these are formed within the solution. It's a mixture of all these 4. So that's why, from an industrial point of view, it is helpful, but not very helpful, because you have to further take further steps in order to separate them. Because if you have a mixture of them, you might not be able to use them properly, because they have different physical properties. That's why you have to be aware that even we say halides, you know, they react with alkanes, although not very reactive, but we have varying levels of products. That's the downside of it. And here, basically, the mechanism of how electrons are displaced, the electron transfer. How does that happen? The molecular electron is broken down to 2 atomic electrons. The atomic electrons are active now, and then they have 1 empty spot for that electron, which is provided by the carbon. Since they are stronger than the hydrogen, they displace the hydrogen first by forming a bond with the hydrogen, and then in the second step, leaving hydrogen alone and coming and sitting at the place of hydrogen, making, and then again, the next molecule would break, and this will continue till the end. So we have radical halogenation here, and what is that radical halogenation? If there is more than one type of hydrogen in alkanes, reactions favor replacing the hydrogen at the most highly substituted carbon. What does that mean? You have the butane here with 4 carbons, all single bonds, because it's an alkane. If it reacts with chlorine, what would chlorine do? Chlorine can sit on the terminal carbon, as you see here, or it can sit on a non-terminal carbon, as you see here. Because in the previous slide, you remember we told that it has tendency for non-terminal carbons because of that pair of electrons, the density of electron. So that's why 70% of the time you will get such because the carbon, most highly substituted carbon, substituted carbon is this one here, not the terminal one. Why? Because it has 3 hydrogens. All the hydrogens are similar from an electronegativity point of view. So that's why you would get 70% of the product as 2-chlorobutane, and then 30% still you would expect or get 1-chlorobutane. This happens more often, and they have in your book how you calculate this. Everything is mentioned. I won't go through this, but just to let you know that the carbon with diverse bonds is much more desirable for halogen than the carbon with less diverse bonds, to make it simple. And then relative reactivity. What does that mean? Based on quantitative analysis of reaction products, relative reactivity is estimated for chlorine. So relative reactivity with a power 5 versus with a power 3.5 versus with a power 1 is expected from tertiary, secondary, and primary molecules. What does that mean? You have this molecule only with 1 radical group. You have this molecule with 2 radical groups. You have this molecule here with 3 radical groups, right? So this carbon is called primary carbon with respect to the radical, perhaps. This carbon is called secondary carbon. This carbon is called tertiary carbon. Now, tertiary carbon has a reactivity factor of 5, while secondary carbon has a reactivity factor of 3.5, and primary carbon has only the reactivity factor of 1, which means this is very reactive. It actively, starts the reaction with chlorine when it comes to chlorine. So as we see here, the tertiary has the strongest power of reactivity. Now, let's say in this case, they got the chlorine. The chlorine here is installed, has made the bond with the primary carbon. Chlorine with the secondary carbon. Chlorine with the tertiary carbon. Now, which one is more stable? The tertiary is now the stable one. The secondary, as compared to tertiary, is less stable, and then this one is the least stable among the all. So basically, this is what we call relative reactivity. 2 different things. First of all, tertiary carbon is more reactive than primary carbon, but a chlorine sitting on the tertiary carbon is more stable than the secondary, and that is more stable than the primary. And allylic bromination. So it means we have a cyclohexene here, right? In the presence of this catalyst, which is called NBS, which stands for N-bromosuccinamide. N-bromosuccinamide acts as a catalyst for this cyclohexene to react with halogens, right? For example, in case of chlorine, that would be chlorination. In case of bromine, that would be bromination, for example. So this catalyst, which is called N-bromosuccinamide, it has a bromine group here in its composition. Now, the final product is shown here, but it goes through a lot of steps, intermediate products. But finally, what you get is these 2 hydrogens, as you see here, they are replaced by the bromine. And then the hydrogen would go and react with the NDS, and instead of bromine you would see hydrogen here. So this new molecule is called 3-bromocyclohexene. The 3-bromocyclohexene goes through a long process with what we call allylic bromination. Now, allylic bromination, and what is allylic? First of all, allylic is, when you start numbering carbons in a ring, you start with 1, 2, 3, 4, 5, 6. So the two opposite positions in a ring is that called allylic position. Now, why do we call it allylic position? Because it is next to double bond first. Secondly, it doesn't matter bromine if you put bromine here or here. They both mean the same thing because there's no difference. It is symmetric. That's why we call it allylic position. They both are adjacent to this double bond. This is the double bond, this is adjacent to it, this is adjacent to it. So with respect to the forces of electronegativity, the same forces are there. They are completely equal with respect to electronegativity. That's why we call them allylic position. I mean, like the same position, similar position. And then allylic stabilization. What is the stability? As we noticed in the previous example, for example, here we have a carbon with bromine, let's say this time. And then we have a primary carbon, which means attached to one radical only with one bromine. And then we have secondary carbon, and then we have tertiary carbon. Which one is again more stable? The stable one is the tertiary carbon because there are no more hydrogens to be replaced by what we call halogens, right? So that's why they are more stable. These hydrogen, they are easily displaced by other functional groups. Here, they reach to the level that it cannot be easily displaced, so that's why it becomes more stable. And then, use of allylic bromination, industrially it is used, it's very important. Why? Because less hindered radical gives major products, and more substituted alkenes is more stable because they don't have more hydrogens to lose. So that's why if we want to get a product which we need to be stable and do not react with halogens anymore, we need to determine ahead of time if we want that secondary alkane to use in this reaction as reactant, or tertiary. If we want the best stable reaction only with one halogen there, we need to use the tertiary carbon because it has no hydrogen to be easily displaced by the halogen group. So that's why we get more substituted, if we have more substituted alkenes, that is more stable. And then preparing alkyl halide from alcohol, the same happens with the alcohol. If you have an OH group making this alcohol, for example, here we have this methyl, one alcohol, and then we have an alcohol with a radical group. Since we have one radical group only for this carbon, that's why it's called primary alcohol, secondary alcohol, and then tertiary, right? So the reactivity increases as you go down for these molecules with halogens. That's why this reaction of tertiary alcohol with hydrogen halide is fast and effective. Why? If you add HCl or HBr gas into ether solution of tertiary alcohol, this is what would happen. You have a 2-methyl cyclohexanol, all because of the alcohol. If you add HCl gas over it, so the alcoholic group would be displaced by the chlorine, and then the hydrogen coming out of the chlorine and the OH here would form the water, and chlorine would be there, forming one chloro, one methyl cyclohexane, the 90% product of it. Let me see. We have one important slide here. I just want to touch base on this and then I'll let you go. Oxidation and reaction in organic chemistry. In organic chemistry, we say that oxidation occurs when a carbon or hydrogen that is connected to a carbon atom atom in a structure is replaced by oxygen, nitrogen, or halogen. It is not defined as inorganic chemistry. In inorganic chemistry, the definition of oxidation was a loss of electron by an atom, right? This loss of electron is not happening here because they have shared electrons. There is no gaining and losing electrons as we see it in inorganic chemistry, forming ionic bonds. Since we don't have ionic bonds here, so that's why the definition of oxidation is different. And that is what in a structure, if it is replaced by oxygen, nitrogen, or halogen, we say oxidation happens. So all the reactions that we saw previously, chlorine, bromine, iodine coming and replacing a hydrogen, sitting and forming a bond instead of hydrogen with the backbone carbon, those are oxidation examples. So even if it replaces hydrogen, the definition is not true for inorganic chemistry where ionic bonds are formed. So that's why oxidation is a reaction that results in loss of electron density, not electron itself, at a carbon. And this is very important at a carbon, as more electronegative atoms replace hydrogen or carbon, because they go replace the hydrogen and they sit instead of the hydrogen. And same wise, organic reduction is the opposite of oxidation. It results in gain of electron density at a carbon. Electron density, not the electron itself, as it happens in organic chemistry. And that's it. Thank you so much.